thank you for the opportunity to present this work. So this work is, let me explain a little bit the story behind this work. So that's a work an algorithm that I developed during my PhD like 10 years ago with Luc Joan as a co-supervisor. But there was a problem, like a particular problem that couldn't solve. So all these years it's been in the background. So one day it's like, oh, what if I try that? So yeah, I had this idea, and then it seems that it works at least partially. So I'm gonna present what we call the extended quantified set inversion algorithm. The quantified set inversion algorithm is already an extension of the set inversion algorithm that you already know. So it's an extension of the set inversion algorithm. So let's see what it is. Well, I guess I don't need to define too much what's quantified real constraint. So it's like a constraint where we have some of the variables that are quantified. So we can have a universal or existential quantifier. So here we have an example, an inequality with one of the variables that is universally quantified. We all know that quantified real constraints, we have lots of applications. Like I'm going to present some applications in robust control that there are other fields where it can be applied. And there are two different approaches to solve these kind of problems. One is the symbolic quantifier elimination. And I know just a little bit about that. So it's basically in a symbolic way trying to eliminate the quantifiers from the constraints, and then we have an explicit solution, a symbolic solution of the problem. And the approximate methods, that is like the one we are going to talk about today, that is basically interval analysis. So you also know that solving big problems in a reasonable computation time is still a very hard problem. It's an open problem, and also like solving the general problem when we have. Here we are going to deal with a particular type of quantified real constraints. So it's what we call like the AE quantified constraints, that we have like always the universal quantifier in front, the existential one. And there are also some other limitations. I don't know, how many of you have heard about model interval analysis? Just curiosity. Okay. So yeah, I mean that's also again an extension of the classical interval theory that you all know probably. Is an extension to deal with quantifiers. So that's a theory that was developed in University of Barcelona and my like home university, University of Girona. And my PhD was basically trying to find practical applications to the theory. So it was a theory, a very elegant, nice theory, but they didn't know what to do with it. So my PhD was like, can we do something with this theory? So like, just like some basic concepts. So in model intervals, we have two types of intervals. We have what we call a proper interval, that's the interval we all know, that we have like the lower bound that is like smaller than the upper bound, like 1, 2. And then we have improper intervals, that is like we flip the bounds. So the lower bound is bigger than the upper bound. So and why do we do that? Because like that we can then assign quantifications. So one of the intervals, we can assign one quantifier, and the one that is flipped, we assign the other quantifier. We'll see that in more detail. Then we have an arithmetic, that the arithmetic is not like just unique to the model intervals. It's what is called the kosher arithmetic or extended interval arithmetic, that we can like do interval computations with these funny intervals that they have these sometimes are flipped. And well, one important operator is the dual. That is the operator that like you flip the bounds of the interval. Well, just to mention that we developed, that was one student that Luke sent me like a while ago. He implemented a nice arithmetic, the model arithmetic or the kosher arithmetic in MATLAB. It's all in like a toolbook, so that's the toolbook that you send me an email, I can send you. So all the model arithmetic is implemented. So we call it the model interval calculator. And well, here it gets a little bit more theoretical, but I'm not going to enter into too much detail. So like the main result of the model interval analysis is what we call the semantic theorem. Basically what it tells us is that we can prove like a logic formula, like a quantified real constraint like this one, where we have some quantifiers in some variables, some universal quantifiers, some existential quantifiers, and we want to prove that this logic formula is true. We can prove this formula using by a simple interval calculation, a model interval calculation. So if we compute what we call the semantic extension of a function over the reals, this f, so we put the semantic extension, we put this star, we call it a star semantic theorem. Then what we do is we have some variables that they range over domains. If you see, when we talk about domain, we put a prime symbol, so that means the domain is not an interval. When we don't put a prime, then it's an interval that can have the modality. So we have some intervals that are proper, as we said before, and others that are improper, depending on this modality. So in this case, if they have the universal quantification, are proper, are like the normal ones, let's call the normal ones, and if they have the existential quantifier, are improper, so we flip the bounds. So by doing an interval computation, if we can prove this inclusion, the outer approximation of this calculation is included in 0, 0, is a little bit weird. In model intervals, we can have an inclusion in 0 because we can have the bounds flipped, so we can prove an inclusion within a 0 interval. I know it's not very intuitive, but it's defined, the inclusion in 0. So if we can prove this inclusion, we can say that this logic formula or quantified constraint is true. Let's see a very simple example. So here we have this quantified constraint, like x plus y bigger than 0. We have for all x within this domain exists y within this domain. So if we put, then we compute, we put proper interval for x, improper for y, we do this simple calculation, and we see that this interval is included in 0, 0. So we can say that this is true. I hope you get the concept. Okay, that sounds very nice, but of course in interval computations, things are not that easy. We have the same problem as in classical intervals. We have overestimation. So when we have multi-occurrence of variables, we also get very overestimated results. So what we did is we implemented an algorithm. It's a branch and bound algorithm. We call it F star algorithm. That what it does is it computes outer and inner approximations of this semantic extension. So that's, again, it's included in these toolbooks, the model interval solver. So it has a very nice and easy to use API. So you define the variables, name, intervals, you can put proper, improper. Then you define the function, you specify some parameters, tolerance, epsilon for the branch and bound algorithm, you call, and then you get an inner and an outer approximation of this semantic extension. And you see it takes five seconds. It depends on the precision you need. But very simple, and you can do computations with model intervals without knowing too much about model intervals. That's available. If someone is interested, just email me. And it's MATLAB. I know probably some of you are not going to believe me, but I implemented the same algorithm in C++, and the computation time is similar. So if you do a proper programming in MATLAB using vectorial calculations, you can get something as efficient as a C++ implementation. So this implementation is quite efficient. I mean, it's not that straightforward. So it's not purely branch and bound of the intervals, because you have the two modalities, the way you have to bisect the proper and improper. So it's quite sophisticated in the background. Okay, so let me quickly introduce the quantified set inversion before we go to the extended version. So you all know set inversion. So it's basically the same idea. The only difference is that the constraints we have are quantified. So we have we define this solution set. There is what we call an A solution set, because we have always universal quantifiers before the existential ones, and basically is a solution set defined by quantified real constraints. So it's exactly the same concept as a set inversion, but with constraints that they have quantification in the variables. So it's same idea. Here is like the restriction. What's the restriction that we have with the original set inversion, quantified set inversion algorithm? Is that the existentially quantified variables cannot be shared. So the same variable cannot appear. So let's say these ones are the existential ones. The same one cannot appear in two constraints, because we can prove that exists for this one, we can prove that exists for this one, but doesn't mean that the same value exists for the two. So they are like two constraints that separate. So you cannot like say that if exists for this one and exists for this one, exists for both at the same time. So that was the main limitation of the quantified. So we were restricted to problems. Oops. Here. Yeah? Okay, so that was the limitation. So let's see. Well, I'm not going to explain that because it's basically, as I said, a set inversion algorithm with quantifiers. With the difference that, of course, like we have the inside and outside rule to prove that the box is within the solution set or outside, that here we have, what we are doing is we are computing the semantic extension every time we want to prove that we are inside or outside the solution set. So if we want to prove that we are inside, we have to compute this outer approximation of the semantic extension. If we want to prove that we are outside, we have to compute an inner approximation of this semantic extension and prove this non-inclusion within zero. Just quickly, an example of what we can solve with this algorithm. So that's classic robust control problem. Well, I'm not going to enter into too much detail. These equations are obtained by the root criterion, so it's like a classic stability problem. So yeah, we have like a set of nonlinear equations. We have these intervals, and we can obtain like a solution set like the one we see, an approximation of a solution set like we see in this figure. Like it takes sometimes 7 minutes. That's not too much more to say. Again, we have a nice API in the model interval solver. You can define the free variables, quantified variables. You can specify here if they are universally quantified or existentially quantified. You define the constraints. I don't know. Am I doing something?
You're touching the cube.
I'm touching. Okay, so yeah, if you want to use the quantified set inversion algorithm, just let me know and I'll send you some code. I already mentioned that the main limitation we have is that when we have existentially quantified variables that are shared between two intervals. How we can solve that? So initially we were trying different ways. So one way would be like to compute the sum of the square of the function. So from like these constraints, we just create a single constraint that is the sum of the squares. The problem is that this is not solvable. So in this case, because this is always positive, we cannot then prove the inclusion in zero. So we would never obtain like an inner approximation of the set. We only are able to compute an outer approximation. So we weren't happy about this approach. And it's also very, very computationally expensive. So the idea that I was talking about before was like, okay, one way to solve this problem, again, is not like generalizing completely the algorithm. Let's imagine like just like the problem with one existential variable that is shared. So basically what we do, that's one of the theorems of the model interval analysis. When we have an existentially quantified variable that is shared, what we can do is we can do the dual in one of the equations, in one of the constraints, we do the dual. So basically what we are saying is it has to exist for one, and for the other constraint it has to be for all. So for one is exist, or the opposite. For exist for this one, for all the one, or the other way. But of course, that's very hard to prove. So what we did is like we implemented another branch and bound algorithm within the QC in order to prove this condition. So basically what we are doing now, so we are branch and bounding like for the QC, 5 minutes, okay, almost. Then when we have what we are going to do then, when we have a box that we want to prove if there is solution, we are going to branch and bound the existentially quantified variable until we prove this condition. That it exists for one, and for the other one has to be for all. So basically, that's the idea. That's one of the theorems of model interval analysis that we forgot. We said like, why we don't apply that, and we built another branch and bound within the branch and bound in order to prove this condition. Of course, this is extremely computationally expensive, but at least it solves the problem that we couldn't solve before. Let's see just an example to see how it works. Let's assume this problem is like another classic problem of a robust control. It's like it's a pole placement problem. It's equivalent to like solving these equations here, this solution set. In this particular case, so we chose this one because we can express the same equations. So if we see here, we have this existentially quantified variable, this one, W, that is shared. So it appears in this equation and in this equation as well. So originally, we couldn't solve this problem. So now with the extended version, we are able to solve the problem. To prove that was correct, what we did is like we chose this problem because then if we can do some symbolic manipulations to eliminate the existentially quantified variable. So in this is equivalent to this, but the existentially quantified variable only appears in this one. Here we removed it. So if we see then the results. Oh, what happened here? You can see it. Sorry about that. So that's the modified version with the original QC algorithm that we see the solution set. And here, unfortunately, we don't see, but we have some solutions here. All these areas are still uncertain. So we realized how hard it is to solve these kind of problems. I don't know if any of you has like an idea to solve these kind of problems in a more efficient way. I would be very happy to discuss about it because it took me 10 years to solve this bloody problem. So I would be interested to know if there's a more efficient way. If you see, I mean, this one takes 8 minutes, and this one in 60 minutes, you only obtain like certain solutions that you don't see. But at least we know that they are proper solutions. But 60 minutes to obtain that. So yeah, that's basically my work. Thank you for your attention. And if you have any question. Anyone has a way to solve that?
No, maybe on your first slide.
First slide?
Yes. You have C element on not the one after. Yes. No. So no, here C is missing on the right.
There's an error. That's not correct. No, C. Sorry, I did some copy pasting of the paper. C is the ones that are shared. So they are both existentially quantified, but I was distinguishing between the ones that are shared and the ones that are not shared between constraints. And this is an error. This should be here.
So it should be what? 0?
No, that was I just saying that is an outer approximation of the semantic extension. But yeah, I got confused here because I was preparing the presentation yesterday. It's too late. Yeah.
Okay, so maybe come back to the problem which is difficult to solve.
The last one. This one.
So it's yes.
So in this paper by Rachan and Bai, they were able to find like one single point that was satisfying that.
Yeah.
But that was it. So
I think it's not so easy.
well, I'm sure there are ways that are not using model interval analysis. I know modeling. I should say model interval analysis can be a little bit controversial. I know some people are not like 100% pro model interval analysis, but I still believe it's an elegant framework to solve these kind of problems. But that doesn't mean you cannot solve it using just classical intervals. But usually you need to do more tricks. So.
As soon as the equations are polynomial, did you try a quantified elimination from the theory of Tarski or Collins?
No.
Is your equation always this kind of? Oh no, this is not polynomial. There is a division.
Yeah. Can be any type of. You can have trigonometric functions, whatever. It's non-linear. Can be anything.
But in polynomial.
Yeah, I mean, I've never used quantified eliminations, but they also have like some limitations, and it's also NP-hard, so it's not.
Yeah, but you only have 6 variables here, 7, 8 with x and x1 and x2, so and only 2 equations.
Yeah, maybe you could solve it this particular one. Yeah.
Yes.
Well, this one is trivial, but we chose this one because it's trivial, because by hand you can eliminate the quantifier. But I mean, here was more like trying to extend and think about the general case. I know we have limitations. We only can have solve very limited type of problems. The complexity. I don't know. Maybe now with the quantum computers we can solve that easier.
So, for this particular problem here, I don't know if it will be better because you check this. But is it now possible to just consider that, kind of traditional branching techniques where you consider you have quantified constraints here? You have a problem here just because you have equations, but equations can be solved with parametric method. And basically what you can do, you just fix the Q1, Q2, Q3 as parameters, as fixed parameters, and you have for all values inside these intervals. And since here you have only 2 existentially quantified variables and 2 equations, you end up with a square system of equations. So, well, with interval coefficients. That's, I don't know if it will be better. That's what I want to
tell you.
But it's another solution.
At least you might be able to find some solutions and then continue.
Yeah, I mean, it depends also what you want. If you are interested in just one solution, or you want to characterize the whole solution set. Yes.
Any other slides? Perhaps we should thank our speaker again.